So in this video, I just want to talk about the lab that we did in class the other day. So in this lab, we were trying to get a really good qualitative understanding of what happens to current in a circuit if you add light bulbs in parallel versus in series. And so we started out with just one light bulb. So just to kind of summarize this lab, we started out with a battery, just one battery, and we had our light bulb. And this was sort of the light bulb that we kind of we made our comparisons with. So we wanted to know, how does this light bulb change when we add another light bulb in series versus in parallel? And so if we add a light bulb in series, what we notice is that both the original light bulb and the new light bulb, they have the same brightness. And I said that in this lab we were going to say that the brightness of a light bulb is an indicator of how much current is going through it. So we said that the current must have decreased. And so if we add a light bulb in series, that must mean that the current going through the circuit must also decrease. And so one of the rules that we kind of made here is that if we add light bulbs or add resistors in series, then the current through the battery decreases. So I'll say that right here. So adding light bulbs and therefore resistors in series. So adding resistors in series, it actually decreases current. It decreases current. And so then by adding resistors in series, we are increasing the total resistance of our circuit. So adding resistors in series decreases I, which means that R increases. And we found the opposite to be true if we added light bulbs in parallel. So when we had our battery, and this time we had our original light bulb, and then we added a light bulb in parallel to that, we noticed that the brightness of the original bulb did not change. So whatever current was going through this original circuit, was the same as the current going through this light bulb, if brightness indicates current, which was the same as the current going through this light bulb. And so kind of obeying Kirchhoff's loop rule, or Kirchhoff's current rule here, so conservation of current, once these two currents sort of meet at this junction right here, then they add up. And so the amount of current going through the battery must have doubled. And so what we can say here is in general, adding resistors in parallel, it ends up increases the current through the battery, which means that the total resistance of the circuit must have went down. So the only reason why current in this case was an indicator, or the only reason why brightness was an indicator of how much current is going through the circuit, the only reason why that worked out with this lab is because we were using identical light bulbs. Every light bulb had the same resistance, and so we could make this assumption. But this isn't always the case. And so we need to really talk about what indicates the brightness of a light bulb. And what really indicates the brightness of a light bulb is the amount of power that it dissipates. So the amount of power that it dissipates. And if you recall from mechanics, power is just how much energy, you can think of it as the change in energy over some interval of time. Okay, and if you do a little bit of derivation here, which I'm not going to do in this video, you would find that power in this circuit here, the amount of power that the battery provides, that's what we're going to talk about first. So the amount of power that the battery provides would be equal to the current going through the battery. So power that the battery supplies is equal to the current going through the battery times the voltage of the battery, delta V of the battery, or the EMF of the battery. So I of the battery times the EMF of the battery. The amount of power, so this is again supplied by the battery. And the amount of power dissipated by our light bulbs or by our resistors or whatever component we have in our circuit here. So we'll say dissipated, the amount of power dissipated by a light bulb or a resistor, that amount of power, so a piece of R, is going to be equal to something similar, I of the resistor, so the amount of current going through that specific resistor or light bulb times the change in potential across that resistor, so delta VR. And if we recall Ohm's law, we can actually write power in different terms. So if we recall Ohm's law, delta V is equal to I times the resistance, IR. We can replace delta V in this case, and we can let power equal I of the resistor squared times R, or we could replace the current with delta V over R. In this equation, we can let this equal delta V squared over the resistance. Okay, so looking at that equation, the amount of power that is going to be dissipated by a resistor, it really depends on a couple of things. It depends on how much potential that resistor is given, and it depends on its resistance. So the higher the resistance of that resistor, the less power it's going to consume. So, and then another way to look at it, the more current going through that resistor, the more power it's going to consume. And in the next video, I want to give you a couple of examples of this.